Hey everyone, thanks for being good sports. Here is our online lecture that hopefully gets you to also sleep through the snow. So, today we're going to talk about using an equation of state for safety. We're going to briefly mention there are other equations of state, and then I want to actually show you the equation for Peng-Robinson. Now remember, what we're trying to do with an EOS, with an equation of state, is to get properties, like if you know P and T, it'll give you density or specific volume, or maybe you want an enthalpy or an entropy or internal energy. Those are all things you can get from an equation of state. The other thing we then can use those is we can now do entropy and energy balances for systems that are not actually using steam or an ideal gas or a refrigerant. So delta H equals 0, say that was a valve, and what's going through your valve happens to be benzene. We can now do that math. And then finally, an equation of state can get us phase behavior. And remember the magic property, it's not magic, it's a thing you calculate. Is when the fugacity of the liquid equals the fugacity of the vapor, that's when you know you are at phase equilibrium for vapor liquid. Fugacity is kind of like pressure corrected to deal with the fact that things aren't ideal. And the final reminder is every equation of state is pretty much telling you how a substance's behavior is different from an ideal gas. So an ideal gas, PV over RT is 1, Z is 1. For every equation of state gives you a way to say what Z is and how Z may or may not be 1 because it's not really an equation of state. Okay, folks, so here's the problem we were starting to set up on Friday. We take a substance and we are curious to know if we are getting a flammability hazard in our lab if we happen to spill some. So the stuff that's at the top of the page we already talked about. I want to just dive in over here and remind everyone there's 3 things you need to have a fire, right? So you need ignition. So usually like a spark or someone strikes a match, something like that. So what we're talking about here is not when things just explode on their own, but when they have ignition. And then what are the other 2 things? Well, oxygen or oxidizer, right? We need some air in the mix. And then, of course, you need fuel. And so fuel is what we're talking about here. And so these things, especially these down here on the bottom, have to be in the right proportion for each other for fire to actually happen. If you have a whole bunch of fuel and no oxygen, nothing happens. If you have a whole bunch of oxygen and no fuel, well, sometimes something can happen. But in general, nothing's going to happen. So what we want to do here is we could do this by experiment. We don't want to do this by experiment. We want to know at what temperature is there enough benzene in the air that benzene could sustain a flame. And that's going to be when benzene has a partial pressure of about that number. So I want you to use the Peng-Robinson equation using the PREOS. You could do it by hand if you're into it, but I recommend using the calculator. And I want you to find 2 things back to back so that you get in your head how these are different. So the first thing I want you to find is the boiling point of benzene, if you haven't done this already, using the Peng-Robinson equation of state at atmospheric pressure. So P equals 0.101325. That's not bar, it's megapascals. So that's the megapascal number. So I want you to go hit pause on this video, go open up that spreadsheet, set it up for benzene if you haven't already, put that number in and see what you get. Then, after you've done that, I want you to do a different calculation using the same setup, which is find the temperature at which benzene hits its LFL. Okay, so hit pause, go do those two things, come back and let's talk about it. Okay, so this is the page where I take you through how I did this with that calculator. So here is our, what we're going to start by working out is the boiling point. And so I have set everything up. I've put 101325 as my pressure. And you see I've got all the stats for benzene up in here. And here you can see that to start, my fugacity ratio is 7. So I'm not at the boiling point. So I'm going to do some changes, and I'm showing you this by screenshots just so it's clear and you can hit pause. So here is another screenshot where I have guessed a different temperature. So I had my initial guess was like room temperature. It's not boiling at room temperature. So my follow-up guess is a bunch warmer than that, right? So you see my next guess, 373, and my fugacity ratio is down around 0.58. So it was 7, then it's 0.58. So my real answer is somewhere between 298 and 373. So let's just take another guess here. I'll show you my next guess. My next guess is around 350, and you see I'm really close. Now that I've gotten really close, I'm going to save myself some work. I'm going to use something called goal seek to get me the rest of the way, to get me a more precise answer. You don't have to do this, but I find this can be quite helpful. So here, I'm using Excel on a Mac. So I use the Tools menu, and then on the Tools menu, there's this thing called Goal Seek. On a PC, it's in a slightly different place. But I go and I open Goal Seek, and when I open Goal Seek, I get something that looks like this. So it says set cell E14, and I want to pick that cell. So I put E14 in there. E14 is the fugacity ratio cell. And I want to set it to value 1. That means fugacity of the liquid, fugacity of the gas are equal. By the way, can you see this here? So Z, very close to 1 there. So that's that's the vapor phase. Down here, very far from 1, so that must be the liquid phase, just so you know. So I want that to get to be 1, and I want it to get to be 1 by changing cell B7, and B7 is where the temperature is. So I'm fixing the pressure, and I'm moving the temperature around till I get an answer that gives me 1. And so I run that, and then it says, hey, is this answer good? And I'm like, yes. So you see my fugacity ratio is exactly 1. And here is that proposed temperature. And that proposed temperature is right around 80 degrees C. And I think what we looked up was 81 degrees C. So that is definitely within our error bars. A good estimate is within 5%. It is definitely within 5%. So go us. So that was boiling point. Make sure you got that. Okay, so now we want to run this equation for solving for it not being boiling, right? Remember, here, let's imagine this is a beaker, and the beaker has benzene in it, and it's not at boiling. It's at some other temperature that's lower than that, right? And think back to Gen Chem and Keg 200. You know that at, let's say the temperature right now is room temperature. Let's say it's 298 K. And if the cup and the air and the benzene are all 298 K, we are at equilibrium, right? Equilibrium is a thing, at least thermal equilibrium is a thing that is happening. And so we know in that case, if we zoomed in and looked near the surface of the liquid, we would see that in fact there is some of the benzene in the vapor phase. Now, you remember how this works. The benzene that's in the vapor phase here is much lower. It has a partial pressure. I'll say P partial benzene, PB. That partial pressure of benzene is lower than atmospheric pressure, because when the partial pressure is atmospheric pressure, do you remember this? It means that it's boiling. That's how we define boiling. So right now we are far from boiling, but there's just a vapor pressure up there. There is some partial pressure of benzene down near that surface. And so it turns out, like that's, we can say if it's at equilibrium, so it's been sitting around for a while, that's its saturation pressure. It's a saturation partial pressure. All right. Do you remember how this worked? You trust me, you did this at one point. So what we're going to ask the Peng-Robinson equation of state is, hey, when the partial pressure of benzene is this, so notice we're not saying we're pulling a vacuum. We're just saying that's the partial pressure of benzene. The total pressure in the room is still like 1 bar. What temperature does that happen at? Okay, so this is our safety calculus. So here, whoopsie, here is, get up here. Here is my screenshot from that. Oh, interesting. It goes behind the picture. Fun. All right. Here's my screenshot from that. So you will see this time, what did I do differently? This time, my pressure is set to that LFL partial pressure. Right? It's the LFL. Okay, I did assume 1 bar is 1 atmosphere, which is not quite right. But let's pretend. So this is the partial pressure when it is possible for a fire to start. And then I did the same process. I iterated until I got the fugacity ratio to be 1. And you see that my temperature at which that happens is right around 295, 296. So that means under room temperature. So let's imagine that you were in the lab. Don't do this. But if you were in the lab and you got a benzene spill on the floor, there's that puddle. It would mean that any ignition source, so someone unplugs a plug and there's a little spark, or there's a plug and there's a spark, or obviously someone drops a match on it, or even the wrong piece of metal hits a different wrong piece of metal, this thing then is flammable. And that's bad. So that's why we work this out. So that's the temperature we just found here is the temperature at which benzene creates a fire hazard when let out. And you'll notice if we go through a bunch of the organics that you might find in the lab, quite a lot of them flammable at room temperature for this very reason from this model. Cool. So make sure, go do that. And in fact, for kicks, if there's anything, I know a bunch of you do research, if there's anything you're working with in the lab, maybe you should work out what temperature it hits its LFL. Ways we work with this safely then is we avoid sparks, we work in the fume hood, we store the stuff with an oxygen-free atmosphere. All of those, very important. Okay, not finally, one more thing, 2 more things. One is that Peng-Robinson is what we're using because it's convenient, but there's a whole bunch of other EOS, and you will see that, go look, a bunch of what you can select as your property packages are equations of state. And they come in a range of flavors. Empirical just means it's a curve fit. It's only based on data. So curve fit. And that means they're only good for what they're good for, but they're really good for that. So like that is the Antoine equation of state tells you, relates a T-sat to a P-sat. It's really good at that. It does 0 other things. It can't tell you enthalpy. It can't tell you free energy. That it doesn't, that's it. Then on the other end, you have something like what's called the van der Waals equation of state. It's really elegant. It's very based on an idea of how the world works. It doesn't tell you squat about actual chemicals. And so most things are a little bit of a mix. They use critical pressure, critical temperature, that omega thing, which is called the eccentric factor. And they, they work for the kinds of chemicals that they were designed to work for. So Peng Robinson is kind of petrochemical-ish. So it does a good job with organics and smaller things, but it's not any good for stuff like acids or ions or polymers. So go shop around. You'll see other equations of state. All right, here we are. We are getting to the final thing. I did just want to show you. Here it is, the Peng Robinson equation of state. This is what you've been solving. This is a screenshot from your book, clearly. I don't want you to write this down. I'm never going to make you solve this from scratch. But if you are into it, go for it. Solve it yourself. So you see here is kind of the simple looking equation. And then all of these three things here, believe it or not, even though they look very complex, those are constants. Those are all constants. So, because this is not pressure, it's critical pressure. This is not temperature, it's critical temperature. So those are things you can look up for that chemical. And you'll notice as it's written here, it's phrased as pressure equals something that's a function of temperature and a function of volume. There's another volume over here, but you could rearrange it and have it written as Z equals. That's a very common way to write it. And sometimes instead of writing it in terms of volume, you write it in terms of density, which is just the same thing but upside down. So there you go. All right. So again, if you are feeling really fired up, go ahead, work this thing into your calculator and solve it yourself to prove to yourself you can do it. And you may also notice this. You're like, hey, wait, we got enthalpy from the Peng Robinson equation of state. I don't see enthalpy in there. Where the heck did enthalpy come from? Enthalpy came from doing Maxwell's relations. So taking derivatives of this equation and manipulating them around. So for example, H is a function of temperature and pressure. So you kind of do dH dt at constant p, and then you write that out, and dH dp at constant t, and you manipulate things around till you can derive a relation that just is based on temperature, pressure, and volume that then tells you about enthalpy. And this is all in your book. You can read it through. I don't tend to go through these derivations here because as a BS level chemical engineer, you're going to go out into the workforce and you are not going to have to derive these. Like you may use them for energy balances, but they will all be existing. You won't ever have to work it out from scratch. If you get your PhD and you are working for Air Products or a petrochemical company where you are deriving new equations of state and new activity models, yes, you will have to do that. But you will have had 6 more years of school to get that together. Okay, last thing. Here's what I want you to, one last little piece of homework here. Please follow the instructions that are up at the top of our Moodle page. So go to Moodle, go to that general class information and regulations thing. And in the software section of that, it says install. It has the link and the instructions for installing remote labs. I want you to do that because we're going to start using HYSYS, actually specifically Aspen properties a little bit. And so I need you to have that accessible. So one more piece of software for you to get. All right, thanks a lot, everybody.